Hello everyone. In this chapters, we are going to study the structure of a protoplanetary disk. Planets are formed in a protoplanetary disk. At the early stage of a protoplanetary disk, gas migrates toward the central stars and prevents solid particles from growing to larger particles due to high-speed collisions between solid particles. Accretion rate of gas slows down when CTTS turns to WTTS. We introduce a disk model around the WTTS Hayashi model in this second section of these chapters. First chapter is CTTS to WTTS. This is a figure of the CTTS. Accretion of gas toward the central star is very active due to the turbulence in a disk. Shear flow due to the Keplerian motions result in the viscous accretion of gas in a disk. This accretion is slowing down with time and turns to the WTTS. In the WTTS, accretion of disk becomes very weak, then sticking of the particles is allowed. Sticking of particles is required to form large particles to lead to the formation of planets. So we consider WTTS growth phase of a planet from a small solid particles. Weak line T-Tauri stars. Size of the disk is about a few hundred AUs. The closest distance to the WTTS we can estimate is 1400 light years from the Earth. Then we can calculate the angular size of the disk is 1.2 times 10 to minus 6 radians. We could convert radian to the arc second it corresponds to 0.25 arc second. Resolution of a Hubble Space Telescope is 0.1 arc second. Hubble Space Telescope has difficulty to find the detailed structure of a protoplanetary disk. Now, ALMA starts working and shows us pictures with high resolutions. ALMA is an international project, Atacama large millimeter submillimeter arrays. It combined many telescopes to gain high resolution image. For example, some dense ring structure were found by ALMA. In the practice 4.1, calculate the angular size of a disk with 100 AU diameters when the disk is located at 1400 light years from the Earth. We'd like to calculate the angle of theta. This R distance from the Earth to the protoplanetary disk is 1400 light years. And the disk size is these 100 AUs. Then we'd like to calculate the theta, d over r. And d is 100 AUs. 100 times 1.5 times 10 to 13 centimeters, 1 AUs. Divided by r is 1400. And 1 light year is 9 times 10 to 17 centimeters. Then you can calculate. It becomes 1.2 times 10 to minus 6 radians. And if we convert radian to the arc second, it's 0.25 arc second. So this is the angular size of a protoplanetary disk. If you observe the protoplanetary disk from the Earth, then we'd like to consider the resolution of ALMA. Resolution of ALMA is 0.01 arc second. So 1 arc second is equal to 1 over 3600 degrees. And then if you convert the degree to the radians, 2 pi divided by 360 radians. And if you calculate, it becomes 4.85 times 10 to minus 6 radians. Highest mountain in Japan is Mount Fuji. Distance between the Tokyo to the Fuji is about R is 100 kilometers. Then we'd like to find out the size of the object on the top of the Mount Fuji when you observe such an object from the Tokyo. This angle is a 0.01 arcsecond. Then we'd like to find the size of this object of the d. D can be calculated. R times theta. Then 100 kilometers times 0.0 arcsecond is a 4.85 times 10 to minus 6 radians. Kilometers 10 to 5 centimeters. Then you can calculate. It becomes 0.485 centimeters. ALMA can recognize the object from the Tokyo's 100 kilometers away from the Mount Fuji. It's a so amazing resolutions. Okay, this is the end of the first lectures.